All right, today we're going to be finishing up chapter 15. We're going to be looking more at mechanical waves, the energy in mechanical waves, and then what happens when waves meet a boundary and interfere with each other. So the first thing we're going to be doing is looking at energy in waves, as I said. So if anyone's been to the beach, you know that waves carry energy. If you've been knocked down by a wave, you definitely know that. If you've been outside, you know that the light waves from the sun carry energy, right? Because it's hot outside. So waves carry energy. And they transport energy from one location to the other, right? The sun transports energy from 93 million miles away to the Earth. So waves can transport energy. And that means that we can talk about the power, because power is energy over time. So if we know that waves transport energy, that means we can figure out how much power a wave has. So let's derive the power equation for a transverse wave on a string. Now, any wave is going to transport energy, but we're just looking at this specific case right now because this is the most common one we're going to be dealing with for now. So let's consider first a wave moving from left to right. So we have a wave going like this, and it's moving from left to right. So its velocity is that way. And now let's zoom in on like a really, really tiny part of the wave. So let's zoom in on like a little part of the wave here. So this is just like a little section of rope that we're looking at here. And now you might remember from maybe 7C that power is the dot product of force into velocity. So if we take the force and the velocity and we dot them into each other, we can get the power. Now here, what's the force we're looking at? Well, the force is going to be the tension, right? So let's look at a specific point A. So we're looking at some point A here. And we want to look at the force that's coming from the left of this point. So the force to the left of this point here is going to be the tension, right? So there's going to be a tension here. And we said last time that any specific point, any individual point on a transverse wave is only executing simple harmonic motion in the vertical direction, right? So this specific point is only going up and down. So on this wave, this point here is just going up and down. So we know that the velocity of this specific point has to be in the y direction. And if you remember dot products, the dot products only pick out parallel components. So if we have our velocity is in the y direction, that means only the force in the y direction is going to contribute here. The x direction will drop out of the dot product, so we only care about the y component of the tension now. So the y component of the tension, so obviously we can draw something like this. So we have the fx and fy. Now let's figure out fy. So let's look at this a little bit more carefully. So we know that there's going to be some angle theta here. And we know also that sine theta is opposite over hypotenuse, right? So let's just write sine theta is opposite, which is Fy, over the hypotenuse, which is just the tension. Or here, I'll write I'll keep everything as tension with a T here. So that's Ty. This is going to be Ty and Tx, just so that's clear. Okay. So now we still need Ty. But if we're looking at very, very small displacements from equilibrium, so again, we're looking at the small angle approximation. So just a very, very tiny piece of wire where the displacement is almost zero, but not quite. We're looking at a very small angle, so we can use the small angle approximation and say that this is approximately equal to theta. And now since we're looking at very small approximations, we can also say that this is going to be about equal to the slope of the rope at this location. So if I just draw this again, I'll have like the rope here, and then we have our point A. There's also some displacement delta y and delta x, right? And then we have the same angle theta. So like I said before, at very, very small angles, these are approximately equal. So now we can use the other small angle approximation. And another small angle approximation is that tan theta is also approximately theta at small angles. So we also have that tan theta is approximately equal to theta. And tan we know is opposite over adjacent. So we have delta y over delta x here. And now I can equate these two things. Since I said both of these are approximately equal to theta, I'm just going to say, well, they're approximately equal to each other then. So now we're just going to say the tension in the y direction is equal to the over the tension is equal to delta y delta x. And now I'm going to do something that maybe some mathematicians wouldn't like, but we're going to change this into a derivative. So we're just going to replace now delta x with dx, even though that's not, like I said, that's what we do in physics, even though you wouldn't really do that in your math class. But we're going to do it. So we have dy dx. Okay, and now we can solve for the tension here. We can solve for the y component, right? So now we have that ty is equal to the tension times partial y partial x. And we know also that the y component of tension is in the negative direction, right? It's pointing downward here if we're looking at this piece. So the tension is in the negative direction, so we're just going to put in a negative sign there. Okay, now we can basically plug things back into this original equation. Now I know that these approximations I made might seem a little suspicious, but physics, we use approximations a lot, especially in scenarios where mathematicians would not be okay with it, but they work and we do it, so that's one thing you're just gonna have to get used to. Okay, so now we can plug things back in here, so let's rewrite. We had power is force times velocity. They're both in the y direction now, so we can forget about the dot product and just multiply when they're in the same direction. So we have the force we said was negative t dy dx, and the velocity we know is dy dt, right? It's the derivative with respect to time. So now we can just, take some derivatives. So we have our equation, y of xt, that we found last time. Oops, kx minus omega t. And so let's take the derivative with respect to x first. So we'll find dy dx is going to be a, the derivative of cosine is negative sine. So we have kx minus omega t, and then the derivative of kx is just k. So we end up with negative ka sine, kx minus omega t. All right, and then let's take the derivative with respect to time. All right, so then we have dy dt is equal to, again, the derivative of cosine is negative sine, so we get negative sine kx minus omega t. And the derivative of inside is negative omega, right? So we've got a negative omega out there. So our negatives cancel and we get omega a sine kx minus omega t. All right, now let's take this and plug it back into this equation here. So I'll just rewrite for clarity. That's an x there. Sorry, no, a y. Then we have dy dt. Okay, so we had negative t, dy with respect to dx was negative ka sine kx minus omega t, and then the acceleration was omega a sine kx minus omega t. And then let's see, we get our negatives cancel, so we have omega k times tension times a squared sine squared kx minus omega t, right? Because we have two sines, so it's sine squared. We had two a, so we get a squared, and then we have omega k and the tension, and our negatives cancel. All right, and now I'm going to replace k. So remember that the velocity is equal to omega over k. So I'm going to replace k with omega over the velocity. All right, and now I'm going to replace the velocity with, remember for our velocity on a string, we had it's equal to the tension divided by the mass per unit length square root. So now we have omega squared, and then we have mu over tension square root, since it was this was on the bottom, so that fraction gets flipped. And then we have tension amplitude squared sine squared kx minus omega t. Now this right here, so t over square root t is equal to just square root t. So now I can rewrite all this as omega squared times, well, let me rewrite that a little bit. I can rewrite it as mu t square root omega squared amplitude squared sine squared kx minus omega t. So this is the power delivered at some moment in time, but usually we want to talk about the average power delivered by a wave. So what we do is we take what's called the time average of sine squared. So basically it's just saying what's the average value of sine over a whole cycle. Now you can see here that if I graphed sine squared would never be negative, right? Because it's squared. So it's always going to be bouncing up between 0 and 1. So that means the average value then is 1/2 because it's always between 0 and 1. So the average value is 1/2 here. So we're going to replace that with a 1/2, and that will be our average power delivered by the wave. So we can rewrite that right here. So this is the average power delivered by our wave. And now it's important to note here that it's always either positive or 0, right? This function can never be negative because sine squared will never be negative. So likewise, the average of it will never be negative. It can only be positive or 0. And it's also important to note that our wave will always transport energy in the direction of propagation. If the wave is propagating from left to right, the energy will always be delivered from left to right. It'll never go in reverse, right? So if our wave is traveling one way, the energy has to travel in that direction as well. Okay, and then a related topic to power is the intensity. So a lot of times when we have a 3D source, like a sound wave that sends waves in all direction, the sun sends waves in all direction, we talk about what's called the intensity. And now the intensity is the time average rate at which energy is transported by the wave per unit area. So it has this additional area factor that we have to worry about. And if we're comparing the intensity between 2 points, we have this relation. I'll show you how to derive that in a second. So this is how the intensity between 2 points is related when you have a single point source basically giving off some energy, and it goes in all 3 directions. And the way we derive this, so let's just talk about power for one more second. So let's just think about power again. So we have a power source here. So this is our power source, and it sends energy out in all directions, right? So it sends energy out like this, and pretend that that's uniform. So as it sends this power out uniformly, as the energy that it is dissipating spreads, since this P is not changing, right? It outputs some set amount of power. As you get further and further away, it sort of dissipates, right? So we have like a circle. You can think of a circle around here. So at this radius r, all of this power originally from the center has now spread out around a sphere, right? A sphere of radius r. So that's what's called the intensity. So the intensity is the original power output divided by that sphere of radius r. So your intensity will depend on your distance from the power source. So this is intensity. As we said, it's power per unit area. And now to get that relation, let's just look at 2 different points that are 2 different distances away. So we have R1 here, and then we have, let's say, some other distance out here that's R2. And we just want to figure out how the intensities between these 2 points is related. So the intensity of the first point at R1 is the power divided by the surface area of the sphere at R1. And then the intensity at point 2 is the same power, right, divided by 4 pi r2 squared. And then we can just take the ratio of these two. So we want to do I1 over I2 is equal to the power of 4 pi r1 squared divided by the power of 4 pi r2 squared. And now when you simplify this, you'll see that the powers cancel, obviously, the 4 pi's cancel. And then I'm left with this r1 squared goes on the bottom, and this R2 squared goes on the top. So then I get left with that should be R2. R2 squared over R1 squared. And that's our intensity relation between 2 points that we just had on the previous slide. Okay, so that's how you solve, we got this. So this just relates the intensity at two separate distances from our source to each other. All right, let's just do an easy example now. So we have an example 15.2. So that was from our cousin Throckmorton from last lecture, who was shaking the clothesline. So we have that set up from that problem. What is the maximum rate? At what maximum rate does Throcky put energy into the clothesline? What is his maximum instantaneous power? Okay, so we have, first of all, we have the linear mass density of the clothesline is 0.25 kilograms per meter, and the tension is 36 newtons. So we want to find the maximum instantaneous power. So that's going to be our power formula that we had here. And the maximum is going to happen when sine squared is 1, right? So when this is at its maximum, we want sine squared to be 1. So we just want this portion of our power equation. So the square root of the mass density times the tension, and then omega squared a squared. So let's just plug those things in. So our power maximum is going to be mu times the tension, and then we said omega squared times the amplitude squared. Now you can just go back to that previous problem where we found omega and we found the amplitude in our previous problem. So we'll so omega we had found was 4 pi radians per second, and the amplitude was 0.075 meters. So that was just from our previous problem. So now we can just plug these in here because we have everything else, right? We have the mass density is 0.25, the tension is 36, take the square root, and then we just square 4 pi radians, and then we square the amplitude as well. And this comes out to 2.66 watts. Remember, power is measured in watts. All right, then what is his average power? So the average power we saw is just half of the maximum, right? So we just have that extra 1/2 from the time average of sine. So we're just going to divide this by 2. So P average is just 1/2 of 2.66, which will just be 1.33 watts. All right, and then for the last part, we want to know, as Throcky tires, the amplitude decreases. What is the average power when the amplitude is 7.5 millimeters? So we can just use the equation we've been using. So now we'll call this P. We have 1/2 mu t square root omega squared a squared. And we can just plug everything in the same as before, except our amplitude will be different. So we're still going to have 0.25. The tension is still 36 newtons. Omega is still 4 pi radians. But now the amplitude is 7.5 times 10 to the negative 3 because it's millimeters. And this comes out to 13.3 times 10 to the negative 3 watts. Okay, so this was an example with power. Now let's look at an example, just a simple example with intensity. So here we have a siren on a tall pole radiates sound uniformly in all directions. At a distance of 15 meters from the siren, the sound intensity is 0.25 watts per meter squared. At what distance is the intensity 0.01 watts per meter squared? So we have our power source right here. Then we know at a distance of 15 meters, the intensity is 0.25. And then we want to know at what distance is the intensity 0.01. So we're looking for I2. Sorry, we have I2 is 0.01. And we want to know what is that distance. So it's obvious that our intensity is going to be less than I1, right? Because if it's further away, the intensity is going to have decreased. So we can just use the formula that we used before, where we had I1 over I2 is equal to R2 squared over R1 squared, and we're looking for R2. So just solve this for R2. We get R2 squared is equal to I1 R1 squared over I2, and then we can just take the square root of everything to find R2. All right, so now we just plug those things in. So we have I1, we said was 0.25. I2 was 0.01, and taking the square root, and then times R1, which was 15 meters. And we get that that comes out to 75 meters for R2. Okay, now we're going to get into some more actual wave stuff. So the first thing I want to talk about is superposition. So superposition is just when you have two waves that are traveling on the same rope or in the same medium. So our two waves overlap, and to find the resultant wave, to find the new wave, we just have to add up the displacements of each individual wave. So here we have our total wave that we see is just the combination of our first wave and our second wave. And you can technically add any number of waves. If you had like 10 waves all at once, you would just have, plus up to y10. So waves just add, and this property follows directly from the wave equation that we saw last lecture. Okay, so this is one important thing about waves that we're going to see how this affects their behavior in a second. So we've got superposition, then we also have interference. So interference is what happens when two or more waves pass through the same region. Again, you've probably seen this at the beach when you have like two waves that are coming in from opposite directions. They kind of like meet and get like twice as big. So that's interference. And you can see here that if we have, let's say, these two waves of different heights, they could be different frequencies too, traveling in opposite directions. So as they come towards each other, they start to overlap, and then their amplitude, their combined amplitude, is actually the sum of each one individually, right? So this amplitude is just like amplitude 1 plus amplitude 2. And then they just keep going and they separate. So they just pass through and continue on. Okay, so let's say I have two waves. So I'm going to draw one here, and then I'm going to draw another one here, and this will be for their resultant wave. All right, so my first wave, let's say, is like this. So it could be any shape. Waves of any shape can interfere. And then let's say my second wave is like this, right? So it's kind of like the mirror image of my first wave. And I want to figure out what is the resultant wave. So right now, so this resultant wave, you would just look at each point on your axis and just add up the amplitudes. So like at my first point here is 0. So, here is just 0. And then as you can see, at each point on my corresponding waves, they cancel each other out, right? So if I go here, this one is some distance above the axis, this one's the same distance below the axis. And that's true everywhere on my wave. So these waves actually perfectly cancel each other out, and my resultant wave would not be a wave. It would just be a straight line. And this is called destructive interference. So when the waves cancel and become 0, then that's destructive interference. And now we can also have constructive interference. So let's say instead I had my second wave looked exactly like the first wave. Then my resultant wave would look the same but be twice as high now, right? It would have twice the amplitude because you add up the amplitudes. And now this is constructive interference because the waves are adding. And now waves can also be reflected, right? You've seen waves being reflected off things, whether it's water waves or light waves are reflected off of windows. So when we have a boundary here, and let's say I have some wave coming in, how do I know what it's going to do when it hits that wave, when it hits that boundary? And with just the information that I have here, I don't know, because I don't know how the wave is going to interact with its boundary. I need to know what is happening here in order to know what the wave is going to do when it hits the boundary. So waves can be reflected when they change medium. So if you have a string and let's say halfway down the string gets significantly heavier, there will be a reflection there. If you're talking about sound waves and you're talking about the wave going from the air to the water, part of that sound wave could be reflected off the water and part of it can be transmitted through into the water. Same thing with light, right? Light gets reflected off of the water, but it also goes through the water. So you need to know how it's going to interact with your boundary in order to know how it's going to be reflected. So let's look at a wave on a string, a transverse wave that's traveling down some rope, and when it hits its boundary, it cannot move. So here it's fixed at the wall. So this point here will not move. Now we can think of this, we can use what we learned about interference, and we can figure out what's going to happen. So let me draw it this way. So if I have some wave coming in here, so if I have so my wave is like this, and it's stuck there. And if this point here is not moving, I can actually model this by saying there's another wave coming in the opposite direction that's inverted. So let's say we have another wave coming, oops, that doesn't look good, like that. And it's coming this way while our original wave is going this way. So what's going to happen as these two waves start interfering? Well, as this wave moves, it might, look a little bit more like that. And then this wave is going to be a little bit less like that. But all the while, this middle point is not moving, because since these waves have exactly the same amplitude, just one is going in the opposite direction and inverted from the other, they're going to perfectly cancel each other out at the boundary here. And then you'll have a point when this one's like kind of flat here, right? When they perfectly cancel, and then as they move through each other, it's going to look like that. So now this one's still going this way, and this, whoops. So it's a little bit hard to do without, trying to draw everything. But basically what's happening is, in order to keep this point from moving, right? I want this point at the boundary to stay at zero displacement. I can make that happen by pretending that there's another incoming wave that will perfectly cancel out my wave on this side. And I can see what it's going to look like happens is that this wave gets inverted. So as this wave moves here, it'll eventually get straight, and then it will reflect off the boundary and get inverted, okay? And this is exactly the same as it looks exactly the same as if I had another wave on this side, inverted, moving in the opposite direction. And now you'll see in a second why I'm making use of this like fake wave basically, to figure out what happened to my real wave. So we'll see that in a second, but we're gonna see what happens first when this is free to move. So now let's say instead at our boundary, the end point of the wave is free to move. So it's like on a little hook here, let's say, and it can move up and down freely. So it's not fixed. I can model this by two waves incoming that have the same amplitude, but traveling in opposite directions. You're gonna see as that happens, they come in, they go up, and they meet at some high amplitude here, and then, they continue going on that way. So this wave is reflected, but it is not inverted, right? It just goes up here, and then it just keeps going back in the same way. It's not upside down. And now the reason that I can make use of these like imaginary waves basically and say, well, I know that they're giving me the right answer anyway, is because of our wave equation. So these were called boundary conditions that we were dealing with when we said the wave is either fixed or it's free to move. That's called a boundary condition. When you specify how your wave is behaving at the boundary, at the reflection point, that's a boundary condition. Now, we have our wave equation, which describes the motion of any wave, right? And we saw that our wave equation was a second-order differential equation. So if any of you are taking differential equations now or partial differential equations, you'll see that when you have these differential equations, you need boundary conditions. You need to specify how they behave on the boundary. And when you do specify how they behave on the boundary, your wave equation, together with your boundary conditions, completely specify your solution. So your solutions are unique. If you have a wave equation with specific boundary conditions, any solution you find is the solution because your solution is unique. So that's kind of what we were doing here, even though we're just sort of, drawing pictures. What we were really doing was saying, well, we have a second order linear differential equation. We have our boundary conditions. So by modeling it as two waves coming into each other, since it matches the boundary conditions, and I know it satisfies the wave equation since it's a wave, my solution is the solution. And the same thing happened here. We found something that satisfied the boundary conditions, and we were able to say, well, that's the solution then, because we know our solutions are unique. But obviously this is not a differential equations course. I'm just telling you that's how we know that our solutions are right. So that's just where our justification comes from. It comes from the wave equation and those uniqueness theorems. All right, so now let's look at a specific example of two waves interfering with each other. So what happens if we have two sinusoidal waves of the same wavelength and the same amplitude traveling in opposite directions along a string? So we have our string here, and let's say one wave is traveling like that, and it's going in that direction, and then we have another wave, maybe let's say going like that, in the other direction. And they have the same wavelength and the same amplitude. So what is going to happen there? Well, all we have to do is just sum up the amplitude at each point, right? Or sum up the displacement at each point, rather. So we can just sum up the displacement at each point to find our resultant wave. And this is, our superposition principle, because we're just going to do y1 plus y2 is equal to the total wave. But remember also that our wave depends on time, right? So right now we're looking here at just one instant in time where this is what the wave looks like. But those waves are going to be oscillating, they're going to be changing, so you have to consider at all times as well. So let's look here for a second. So let's say we have this wave here is moving to the left, and this wave is moving to the right. So you just add up their amplitudes like we said, and you can see their amplitude will be twice as big because they perfectly line up here. So this is at like t equals 0. Our amplitude ends up just being twice as big. But now a second later, let's say, this one's moved a little bit more to the left, and this one's moved a little bit more to the right. So now they don't perfectly constructively interfere with each other anymore, and they actually perfectly cancel each other out, right? Here we have the maximum, the maximum displacement downward, and here we have the maximum displacement upward, so those cancel to 0, and that happens at every single point. So here we have maximum destructive interference because the wave ends up just not being a wave anymore, right? It's just a straight line now. Now 1 second later again, this one's moved more, this one's also moved more to the right. So now the wave looks like this. We're just adding up point after point after point. And then, you keep going all through a whole period until you get to here and they're back to their original position. So you can see here, imagine this was like animated and we had it going through time. First it looks like this, then it looks straight, then it looks like this, then it looks straight again, then it goes back to its original position. So the wave is obviously oscillating as we go through time. And so this is called a standing wave. So a standing wave doesn't itself move to the left or right. It stays perfectly fixed between two endpoints, and it just oscillates within those endpoints. So this is a physical example here. So if we were fixed, it's fixed here and here, and it just oscillates up and down here, and oscillates up and down here, and oscillates up and down here. But the wave itself isn't actually traveling to the left or right. All right, now you can see here in this little example here, you can see that there are some places that are oscillating between the maximum here and then the minimum down here. And then this point doesn't really look like it's moving, right? So these are called nodes and antinodes. So if I have a standing wave, let's say it's fixed at 2 points. So I have my rope here, and I have my rope, it might maybe look like that, and then it's fixed there and fixed there. And it will sort of just oscillate like that. And this is called a node. So each one of these here, these points that are not moving, are called a node. So this is a node, this is a node, this is a node. These two endpoints are nodes because they're not moving. If the displacement throughout the oscillation of the standing wave is 0, it's a node. And then an antinode are these points up here that are oscillating the full amplitude up and down. So these are called antinodes. So this is an antinode. And this is an antinode. So all those are antinodes. All right, and we can obviously make an equation to describe a standing wave as well. So the equation for a standing wave is given by this. So it's twice the amplitude of each individual wave. And then we have sine kx, where k is the wave number of each wave, and then sine of omega t. So we have two sine functions in here. And remember, the waves have the same lambda, which means they have the same k. And each wave also has the same amplitude. All right, so now what I want you to try to do is try to derive this equation yourself. So deriving equations is like super important in physics. It's a really great way to study because you'll really learn the equations really well if you are working with them a lot and manipulate them a lot. So I highly recommend deriving as many things as you can in the textbook regardless. But anyway, so take what you know about waves already, right? We know how to write the equation for a wave traveling to the left, and we know how to write the equation for a wave traveling to the right. So take one wave that's going from left to right, and one wave that's going from right to left, but inverted, and then try to combine them and try to get to here. Okay, so I'm going to throw up some trig identities because you're definitely going to need some trig identities. So you'll have to choose, see which one's appropriate, choose the right one, and then manipulate your equations a little bit and eventually get to here. Okay, so I'll give you a second to do that, and then we will do it together when you're done. Okay, so we said to get the standing wave equation, we have one wave that's traveling from left to right, and one wave that's traveling from right to left. So let's do our first wave going from left to right. We'll call that YL. And that's going to be our normal wave equation or wave function that we saw before. So we have A cosine kx minus omega t, and that's it. And then the one going from right to left, we'll call y sub r. That's going to be negative, right, because it's inverted, we said, so it's inverted cosine kx, and then it's traveling from right to left, so it's traveling along the negative x direction. That gets a positive there, so we get positive omega t. Okay, and now we just use the superposition principle and we just add them up to find our total wave. So our y total will be, I'll pull the a out, and we get cosine kx minus omega t minus cosine kx plus omega t. And now we have to use one of our trig identities. So the trig identity we're going to use is cosine of a plus or minus b is equal to cosine a cosine b minus or plus sine a sine b. Now, in case you've never seen this notation here before, where you have plus or minus and then minus plus, that just means when you have plus on the top here, you use the minus over here, and when you have minus, you're using minus down here, you use the plus down here. So that's all that means. Okay, so now we can use this trig identity to rewrite what we have in here. So we're going to use this where A is kx and B is omega t, and then just rewrite it using this. So I'm going to forget the amplitude outside now, so we're just going to ignore this for a second. So we have cosine of kx times cosine of omega t. And then we have plus, because here it's minus omega t, so we use plus down here. So then we have plus sine kx sine omega t. Then we're subtracting, we're going to replace this term and use this, so we get a minus sign. So we have minus, now it's going to be cosine kx cosine omega t. And then since here now we have plus omega t, so it's plus, we use the minus sign over here. So then it's going to be minus But remember, we're subtracting. There's a minus sign outside this entire term, right? We had a minus sign outside everything here. So we have a negative, negative, so this term is actually a positive. So we have positive sine kx sine omega t. And now we can see that this term and this term cancel because we have cosine minus cosine, and then these two add up. So we get, no cosine, so we get 2 sine kx sine omega t, and then there's an amplitude out front that I was ignoring for now. So now we get for our full equation 2a sine kx sine omega t, and that was our standing wave equation. Okay, so that's how you derive that from our wave functions. All right, now let's move on. So back to nodes and antinodes for a second. So we can use the standing wave equation to figure out the location of our nodes and antinodes. All right, so let's say I have some standing wave like this, and let's say it's fixed at each end for now. Doesn't have to be, but let's say it is. And this is our x-axis here. Okay, so we want to find the location of the nodes using our standing wave equation. So we have 2a sine kx sine omega t. And we want to find where on our wave are the nodes. So remember, the nodes are right here. The nodes are where the displacement is always 0, right? So they never move from the x-axis. So that's going to be in here, right, in this x part of our standing wave equation, because this sine omega t here will be what oscillates things up and down. So we're just going to say, okay, sine kx is equal to 0 where? Well, you can look at your sine function, and you can see that your sine function is 0 at intervals of pi, right? So we have a pi, we have 0 there, and then pi, then we have 2 pi, and then, we'll keep going to 3 pi, and so on. So sine will be 0 at intervals of pi. So let's say that's going to be 0. So sine of kx will be 0 when kx is equal to an integer multiple of pi, right? N times pi. And now let's solve for x to figure out where that actually happens. So x is going to be n pi over k. And now if you take any upper div physics class, you're going to be doing this a lot. So you have x equals n pi over k. And now let's change from k to the wavelength. So remember, k is equal to 2 pi over lambda. So I'm just going to replace k with 2 pi over lambda. So that's going to give me n pi over 2 pi lambda. So I can see my pi's will cancel, and I get n lambda over 2 here, where n is some integer. Okay, so these are the locations where there will be a node, and you can do a similar thing for an antinode, figure out where is sine going to be equal to 1 or negative 1, and you can figure out the same thing. But usually we care about nodes more than antinodes. So our locations of our nodes in terms of the wavelength will be given by this. It'll just be integer multiples. I should really write plus n lambda over 2, okay? And this makes sense because you could see when we drew a picture before, so when we had it like fixed at both ends like this, and we had our standing wave like that, and you could see that every half wavelength, right, there was a node. There was a point that wasn't moving, because this here, from here to here is one full wavelength, and we had a node halfway in between. So every half wavelength, we have a node. All right, now one important thing about standing waves is that they don't transfer energy, right? If I have, a wave here that is transporting energy in this direction, but then I have another wave with exactly the same amplitude and exactly the same frequency traveling in this direction, I'm not going to transfer any energy, right? So a standing wave can transfer energy like between points within the standing wave. So like if you want to transfer it from here to over here, it can do that. But your average energy, your average power for a standing wave will always be 0. Because any energy that you transport one way will immediately be transported back the other way by the other wave in your standing wave. And we should note that this formula is valid for a wave on a string that's fixed at least one end. It can be fixed at both ends, but it has to be fixed at least one end for this to be valid. All right, now let's do another example. So here we have a guitar string that lies along the x-axis. The end of the string is fixed. We have, let's say, the amplitude is 7.5 times 10 to the negative 4 meters. Okay, and it's traveling in the negative x direction at 143 meters per second. Okay, so we end up getting a standing wave from this string, and we want to find the equation of that standing wave. So that's easy. We can just write our standing wave equation we had here, and then just find k and omega. So all right, so this is our standing wave equation. So we want to, let's find k first. So k, remember, is 2 pi over lambda. So let's find omega first, since we already have the frequency. So omega is 2 pi times the frequency, so that will be 2 pi times 440 hertz, which will give us 2,760 radians per second. So that's our angular frequency. Now we can find, we need to find k next. So k, remember that the velocity of a wave is equal to omega over k. So we can just rewrite this and solve for k. We get that k is equal to omega over the velocity. And now we have omega is 2,760, and the velocity is 143. So that gives us 19.3 radians per meter. And now we can just plug those into our equation since we have the amplitude. So we have that y is equal to 2 times the amplitude. So that's 2 times 7.5 times 10 to the negative 4 sine of k, which is 19.3x, and then sine of omega, which is 2760 times t. And that's our equation for our standing wave. Now that's part A. For part B, we want to locate the nodes. So I'll add another page in here. So to locate the nodes, we remember our equation for the nodes. The nodes were located at 0, lambda over 2, lambda, and 3 lambda over 2, etc., etc. So first we need to find the wavelength, obviously. So the wavelength, remember, k is equal to 2 pi over the wavelength. So that means the wavelength is equal to 2 pi over k, which is 2 pi over 19.3, and that gives us 0.325 meters. So our wavelength is 0.325 meters. And so now let's just plug that into these equations and let's find our nodes. So our nodes, we have one at 0, then we have one at 0.325 divided by 2, then we have one at 0.325, one at the wavelength, because that's 2 lambda over 2 just gives us the wavelength, so it's 0.325, and then we'll have 0.325 times 3 over 2. So this gives us 0, 0.163, 0.325, and then 0.488 meters. So that's where our nodes are. And then let's see. For part C, we want to find the amplitude of the standing wave and the maximum transverse velocity and acceleration. So the amplitude we kind of already found. It's just 2 times the amplitude of each wave, right? So the amplitude, so this is part C. So the amplitude is just 2 times 7.5 times 10 to the negative 4, sorry. So that gives us, we end up with 1.5 times 10 to the negative 3 meters. So that is 1.5 millimeters. So this is the amplitude of the standing wave. It's twice as big as the amplitude of each individual wave that makes it up. And now we want to find the maximum transverse velocity. So we can use our velocity equation from chapter 14. Remember, we had V max is equal to omega times the amplitude. So we can just plug that in. We know omega and we know the amplitude. So omega, we said, was 2760. And then the amplitude here, you want to make sure you use the amplitude of the full standing wave, not one of the individual waves. It's the full amplitude. So we're using this amplitude that we just found. So times 1.5 times 10 to the negative 3. So that gives us 4.14 meters per second. So that's pretty fast. All right. And then we want to find the maximum acceleration. So we can use the same equation from chapter 14, but for the acceleration. So we had A max was equal to omega squared times the amplitude. And we do the same thing, 2760 squared times the amplitude of the full standing wave, which is 1.5 times 10 to the negative 3. And that comes out to 1.14 times 10 to the negative 4, sorry, 10 to the 4 meters per second squared. And that's our acceleration, okay? All right, so that's it for that problem. So now let's go on. So let's consider a string of length L fixed at both ends. So that was kind of like what we had drawn before, where we had a string that was fixed. So it has a node at both ends like that. Oops. Okay, pretend that looks good. If it has some length L, and we know that there are nodes every half wavelength, and we know that there's a node at each end, we can figure out what are the allowable wavelengths for this standing wave, right? So let's, we had our equation for the location of the nodes, we said was x was equal to n lambda over 2, where n was some integer, but now x is L. So we want to say whatever point this is here, which is L distance, down the x-axis from 0, this is a node, right? Because it's fixed at both ends. And now let's figure out what are the allowable wavelengths given this L. So let's just solve for lambda here. So we're just going to solve for lambda. So we get lambda is equal to, so we get lambda is equal to 2L over n. And I'll put a little sub n there. So this is the wavelengths that will be allowable on this string. Because here you can see I have like 1 wavelength, 2 wavelengths. So here I have 2 wavelengths. I could just as easily put half a wavelength, right? I could make a standing wave that's just like that, where there's only half a wavelength. Or I could put, I could put a lot more. I could put like that many, right? But I can't put any other value. If I want to have a standing wave that has a node at each end, I don't have a choice that other than to use a wavelength that meets these criteria. Now, you could obviously put wavelengths of, you could put any wavelength on some string. You just won't necessarily get a standing wave from it. So if you want to get a standing wave, you need to have a wavelength of this that satisfies this equation. Okay, so I just rewrote that here. So this is just our previous formula we just had, where n is any integer. And now we can also, when we apply this like musical instruments, we can find out what kind of frequencies are allowed. So So let's take this equation and turn it into a formula for frequency. So we had lambda n is equal to 2L over n. And then remember that the velocity and the frequency are related. So the velocity is equal to the frequency times the wavelength. So I'm going to replace the wavelength with the velocity over the frequency. So now I have velocity over frequency is equal to 2L over n. And then let's solve for the frequency. So the frequency is going to be n times v over 2L. And I'll make a little subscript here for f sub n. So these are my allowed frequencies if I want to have a standing wave with a node at both ends. And now these are sometimes called harmonics, the harmonics. So you'll see that a lot, like I said, for like musical instruments and stuff. So these are our allowed frequencies called harmonics. And when we have n is equal to 1, that's called the fundamental frequency. So that's like the minimum frequency that you can have on a string of a certain length. And then sometimes the frequencies where n is greater than 1, you'll see referred to as overtones. And this is also related to something called normal modes. So normal modes you'll see a lot if you take like advanced mechanics. You'll be doing a lot of normal mode stuff. But normal modes just mean that every point on your system is oscillating with the same frequency. And then here also we just have some diagrams of the fundamental frequency and some overtones. So like I said, n equals 1 is the fundamental frequency. N equals 2 is then called the second harmonic or the first overtone because it's the first tone over the fundamental frequency. And then it goes on, you get to the third harmonic, fourth harmonic, etc., etc. Okay, so we can also take our equation for the harmonics and replace v with the equation we know for velocity on a string, right? If we take, let's say f is equal to 1, so let's say take our fundamental frequency. We have the velocity is equal to 2 over L. We know the velocity for a string, right? So I can replace v with the tension divided by the mass per unit length square root. And I can just get now for my fundamental frequency, the tension over mu square root. And so we can have this equation for our fundamental frequency, which I wrote here. And again, this is for a string fixed at both lengths, so that's very important. Okay, so now we have all of these equations. So let's do one more example. So we build a double bass with strings of length 5 meters. So our string length is 5 meters between fixed points on a string with linear mass density. So the linear mass density is 40 grams per meter, which is 40 times 10 to the negative 3 kilograms per meter. And the frequency is 20 hertz. We want to calculate the tension in this string. So we know the fundamental frequency, we know the length, so we can figure out the tension, right? Because we just had this equation. So, oops, that's a T. So we can, let's square everything and then solve for T. So we can square everything. We get the frequency squared is equal to 4L squared T over mu. All right, so now we have the tension is equal to F squared times 4L squared times mu. And we just plug everything in. So we know that the frequency we said was 20 hertz squared, 4 times the length squared, which is 25. And then mu we said is 40 times 10 to the negative 3. So then just plug these things into your calculator and you will get 1600 newtons. So this is the tension. And now we want to know the frequency and wavelength of the string on the second harmonic. So the frequency of the second harmonic, so our harmonics are given by NV over 2L. So you can see here that if you know the fundamental frequency or the first harmonic, you can just multiply by n to find all the other ones, right? So since we know the fundamental frequency is 20 hertz, we can just say, well, the second harmonic is just 2 times 20, right? It's just 2 times the fundamental frequency. So that's obviously going to give us 40 hertz. And then we also want to find the wavelength associated with this. So the formula for the wavelength was lambda n 2L over n. So here we're looking for n is equal to 2. So you can see if we plug in 2, we just get that lambda is equal to L. And we know L already, right? They said that L was 5 meters. So our wavelength for the second harmonic is just 5. And now let's look at part C. So part C then is the frequency and wavelength on the string of the second overtone. Now remember here that the second overtone actually corresponds to n equals to 3. If you see here, the third harmonic is the second overtone, because remember it's over the fundamental frequency. So the second overtone is n is equal to 3. So we're basically doing the same thing, but n is equal to 3 now. So we want to find for part C, let's find the frequency first. So the frequency, as we said before, is just going to be 3 times the fundamental frequency, right? Because they go up by n, so they go up just every integer. So we can just do 3 times 20 is equal to 60 hertz. So that's the frequency of the third harmonic, or the second overtone. And now for the wavelength, we can do lambda sub 3 is 2L over 3. So we do 2 times 5 over 3, and that will give us 3.33 meters. Okay, and that is our frequency and wavelength. Okay, so that's it for today. Next week we're going to be looking at longitudinal waves a little bit more, like sound waves. All right, so I'll see you guys then.